Here we're going to continue our study of how functions change. And we're going to continue to play with this idea of looking for patterns in outputs as we allow inputs to approach certain numbers. Okay, so in this case, obviously, as x2 approaches 6, the slope of the secant line approaches 2, right? And that's pretty obvious just from how the table looks, right? These values on the left are approaching 6. These values are approaching 2. Okay, so the slope of the tangent line, so if these are all secant lines, the slope of the tangent line is, we'll say the tangent line has a slope of 2 at x equals 6. Okay, so this mode of analysis is new. And as is often the case in your math career, when you learn a new technique, it comes with some new notation, right? So we have some notation that describes these trends of what happens when an x value approaches a certain number to the function, right? So we're going to use what's called limit notation. And this looks scarier than it is. What's going to help you learn this the best is by reading these out loud. Or if you're in a quiet classroom, you don't want to do that, you can read them in your head. But reading these and thinking about how to say them is the best way to get comfortable with this notation. So here, in limit notation, I'm going to say the limit as x2 it's called, approaches 6 of the secant slope equals 2. So this gives us a way to say, like, no longer are we just talking about, like, this looks like it gets close to 2. This gives us a way to say that this particular property equals 2. Okay? So again, one more time. The limit as x2 goes to 6 of the secant slope is equal to 2. So take a second to just read that to yourself or read it out loud if you can. So let's clarify this notation a little bit. So here's just a general example for your notes. So we'd read this as the limit as x approaches a of f of x is equal to L. Okay? Now, x approaches a, this is the easiest part. So this tells us what x value the function, or we are interested in. What x value are we approaching? And then f of x, well, that's what we're interested in studying, right? So f of x is what we are investigating. Okay, and then L is the value that that function is approaching. So we're going to write that in a certain. So this says that as x approaches a, so x gets close to a certain value, f of x, so the function itself, the y value, approaches L. So L is like the result or the answer. Okay, make sure you have that down in your notes. Now is a good time to pause and make sure you've captured all this before we move on. So now we have an example. So take a look at this table. It says describe the behavior of the function near x equals 0 using limit notation. Well, x equals 0, here's x. X equals 0 is here. And notice it's undefined at x equals 0. So maybe it's a function where x is on the bottom of our fraction. So whatever it is, when we plug in 0, we can't get an answer out of f. But we can say what happens as x gets close to 0. Right? So x gets close to 0 from the left. So we get closer and closer to 0. And from the right, we get closer and closer to 0. And notice in both cases, from the left and from the right, we're approaching 1.66. Okay? So the way we would write this down, it says describe the behavior of the function near x equals 0 using limit notation. We would say the limit as x, what is x going to? Well, x is approaching 0. The limit as x approaches 0 of f of x, so f of x is what we're interested in, equals, and now we say the limit. So f of x is undefined, but the limit of f of x as x approaches 0 is 1.66 repeating. Okay, so this statement describes what's happening in the table. So our main idea here, and this is super important, so we can use this notation to describe what happens as x approaches a certain value, even if that function is undefined, right? So now we have a way to talk about how this function behaves, even if we can't get a certain, if it doesn't spit out a number at a certain x. So this connects to our goal of analyzing the slope at a specific point on a function in a really profound way. So let's look at a problem now that we've seen before. So we have our race car problem. So the position of the car is given by this function, and now we want to write that expression, you've done this before, for the slope of a secant line on this interval from 1 to b. Well, our secant line would be s of 1 minus s of b over 1 minus b, right? And then we could make that substitution. So s is t to the fourth, right? So we'll get 1 to the fourth minus b to the fourth over 1 minus b. And we know, of course, that 1 to the fourth is just 1. Okay, so here is my expression for my secant line. And remember, we talked about this idea of using the interval, of letting b equals 1, essentially. So we're looking at the interval 1 comma 1. Because our tangent line only touches the curve at one particular point at t equals 1. So that's our tangent line. Notice the problem we run into here. So if I try to plug in b equals 1 into my expression here, or if you just try to do, 1 to the fourth minus 1 to the fourth over 1 minus 1, we get a denominator equal to 0. Okay, so if I try to use my secant line formula, my slope formula, to find the slope of a tangent line, I always get a denominator equal to 0. But what we can do is, instead of saying b equals 1, we can't say that because we can't plug it in, but we can say we're going to make b approaches 1. Okay, so we have this expression for slope, and then we're going to look at what happens with that expression as b gets closer and closer to 1. So here is our limit notation. We want the limit as b approaches 1 of 1 minus b to the fourth over 1 minus b. And this is no longer now the slope of my secant line. The answer to this limit would be the slope of my tangent line. Now, we don't know how to solve this yet, but we're going to build towards some methods of solving these limits because they help us find the slopes of these tangent lines and help us analyze how quantities change. So the reason we need this idea of limits is that every time we try to find a tangent line, if we try to do it this way, using our slope formula, we get a denominator equal to 0. Because there's only one point that it touches the function at, right? So the main idea is that every time we find the slope of a tangent line, we're actually taking a limit.